Yeah, so I'm not a games developer at all. I'm very much a gamer, and I've dabbled in doing game mods back in the day, so Half-Life mods and Tries 2 with some friends of mine who went on, I think as I said in my bio, they went on to become actual games developers at THQ, and a friend of mine was at Chrome for a number of years. So yeah, but my thing is, I guess I love using functional programming. A few years ago I was introduced to Haskell in the course of my Java day job, and it really seemed to be like a great way to write programs and get them to run correctly, with not many bugs, very concise, and all this sort of stuff. So I really latched onto it, and yeah, so this is a presentation mostly about how I wrote this very particular game. There is Haskell code in it, so I'll talk through what it is, because I think there's probably no one here, maybe one or two, who've seen a bit of Haskell. So, but it's not too bad. Maybe 5 lines on the screen, as much as we'll see it once. And if this works, I can control it with this. So everything I just said. If you're aware of what functional reactive programming is, we're going to see a bit of that. But that's kind of a term that covers so many different technologies in not a very clear way. I wouldn't take what this is as being FRP, but just be aware that maybe this, if you end up getting into that kind of thing, because a lot of actual game engines that run on functional programming languages end up talking about that. So anyway, that's it. So 2 apps. One is the game. I'll give you a bit of a demo about that, and one is the presentation that I'm giving today. So this is written with SDL, and Haskell. Not done using the same tools that I was knocking the game up over the weekend that I did it in. So I'm using SDL mostly just so I can draw rectangles and get inputs. That was all I kind of needed to be able to do simple games, right? And I'm using a library on Haskell called Netwire, which is this FRP sort of thing. And it's really about modeling values that change over time. So when you're building, I'll get into that in a second. So primarily, if you're not really much of a functional programmer, I know Charles won't be much of a reference for you. But I went to Camp.js, which is a weekend hacking, a hack weekend, I guess. You're there from Friday to the Monday, and it was just an opportunity to sit down and really sort of just latch in and prove out whether this would actually work, writing a game in Haskell. So I'll show you what I've done.
I thought that was hilarious. You built a Haskell game at Camp.js.
At Camp.js, yeah. Yeah. It's funny because I've been to Camp.js and Rails camps, the Ruby equivalent, for a while. And at the Ruby camps, I've written JavaScript generally. This was, a chance to practice my front-end skills with a bunch of sort of really hot Rails programmers in the room to do the back-end things. So now as a JavaScript, it was time to step up into Haskell, I guess. I might get a couple of people to play so I can talk about it actually. So if you two guys want to jump on here. Your controls are WASD to drive thrusters and shift for turbo, and yours are arrow keys and shift again. That should be on it. So this is what I did in the weekend. Little lunar landery kind of thing. It's called flying sheep battles. The goal is to smash the sheep into the other sheep. So the red line is the blood kind of splat. That sheep got squished. That's pretty much it. And it just runs and runs and runs. Bigger thrusters for holding down shift for turbo, etc., etc. There's a bit of vector maths going on when you collide. It's the component in the direction of the other sheep that matters, not just your sort of magnitude. Really terrible collision detection with the downing box and the big golden rod divider in the middle. The thing we'll probably talk about most today is how the background is built. So, because it was sort of the thing that I spent the most on in the end, Netwire has lots of cool functions for dealing with objects that move. We'll see a bit of that. But the fact that there's kind of a day-night cycle going on where the background color is changing from light to dark, stars appear, and they're sort of graduating in color according to height, and then they disappear as midnight passes, and we start getting through to sort of 5 a.m., and they do fall into the ground. Yeah. There's a routing error. It's fine. You can bring them back up, but they get stuck. And the cloud is just nothing. So, this one. All right, so kind of 5-ish sections. I'll talk about how functional programming kind of fits into games, and a little bit about what functional programming is when I start talking about that kind of thing. So the very specific functional programming technology I'm using to build the game is called the wire. Coming from the library, we'll look how we built the sky, building it up, layering it on, and same with controlling an object around, and then the problems I sort of had, which were mostly kind of system and tooling sort of things, which is a little bit about, I think, what John Carmack starts to say the problems with doing anything in Haskell is a little bit the tooling, a lot of library support and things like that. So, a functional core. Let's skip over to this maybe for a little while. So when I talk about functional programming, there is a very strict definition. So we're talking about programming with mathematical functions. So these are not methods on objects. These are not procedures. A mathematical function always produces the same output given any input. So it can't have any mutating internal state. It can't read from, system keyboard or the gamepad or anything like that and produce a different output. If it's a mathematical function, then it can only deal with its inputs and some kind of constants within the system. It can't actually, sort of reference anything else. So pure functional programming can't talk to the outside world. And also, we have to be able to pass functions around its values because that's the only kind of tool we have to work with. So pure functional program, typically you don't have sort of, objects encapsulate state or things like that. As we'll see, we kind of end up passing functions around returning new functions that encapsulate new state and then sort of calling those kind of things. So we can pass state around, we just kind of change it inside ourselves and keep a hold of that change. So what has sort of come up from outside functional programming circles is building programs with a functional core and an imperative shell. So you do all your interaction with the real world right at the edge of your program, and you try and do as much as possibly you can in your functional world, pure world. So see some examples of functional cores in other kind of technologies. So if you're writing a web app, your functional core might be a function. So the way to read this is a function name, web app, and colon delimits it with a type signature, and everything up to the last arrow is an argument, and on that side is the return value coming out the other end. So this is a function web app that takes in a request as its argument and spits a response out the other end. Feel free to fire questions at me, by the way. We've got a heap of time. I think the talk takes about half an hour, so if you want to get me to clarify anything, or I'm happy to take interruptions.
Is there a specifier like types at all?
Sorry?
The input and output? So
this is specifying, this is the type signature, this is not naming the arguments that will be used later.
Okay.
So typically there'd be a definition as well that would reference that. So in Haskell, the type signature is separate from the implementation. Rather, in sort of Java, C# where it's sort of tied in, you would name the particular parameter at the same time. So web apps, right? You would read the request in your imperative dirty world that you pretend doesn't exist. You'd read the request off the socket and pass it, and then you'd send it into your functional core, which is a function that just produces the response, and then back in your imperative dirty world, you'd start streaming the response back out over the socket, right? So, but generally on the inside there, maybe you have to pass a bit more data through, maybe you have to deal with databases and things like that, but we can sort of pretend that doesn't exist and just say that on the inside, request comes in, we produce a response purely, and then at the edge is where the side effects kind of happen, and we can edge that. So we can do that for web apps. Sort of with databases, you can imagine you pass queries in and you just get result sets back out, and inside that, you don't really make any changes with the database query.
Isn't the database external state though?
Yeah, so then with the database update, right, it gets a little bit tricky to represent purely functionally. You sort of have to pass in what you want to change and the original database and get a whole new database out the other end that would have the change on it. So changing a database is inherently a side-affecting process.
Just even with the query though, just for my own sort of understanding of how the functional side works, does that mean, wouldn't the database have to be an argument to the database query?
Yeah, it probably would.
Okay, right.
Yeah. Assuming that nothing else has changed. Well, so yeah. Also in Haskell, a type signature like this means that I'm not talking to the outside world. There would actually be a marker on this part that would say that to produce the result set, I had to talk to a database, and that would be represented here through a type parameter, a little bit like a generics sort of thing if you've done any C# or Java. So there would be there'd be a marker on this. There'd be a marker on this type that would delimit that there was an effect, that like some sort of external effect to produce it. And that
So
would
it sort of flags the function as impure.
yeah, exactly. Yeah. But the way I represent it there, I'm saying it's pure in the database as a constant somewhere, and we can sort of reference it. Yeah. So the way I'm sort of dealing with the functional game core. So I'm not going to talk too much about the bits on the edge, the imperative start and finish of the game loop, because it's for a very simple game. It's I'm just doing the naive way. I'm pulling. I've got a loop that pulls events off in SDL, storing them in set, and then I do my little functional core that steps our game state, which is this bit here, and then the rendering is all again dirty imperative kind of world. So I'm not going to worry about those bits because they're the bits you edge. And what's really cool is the bit on the middle where you can do pure functional programming and not have effects, and get a whole bunch of benefits in that for sort of parallelism and being able to reason about your code and things like that. So the game loop becomes read the events off the system, outside, so that can be either events that have been generated by your previous frame or from your network or your controllers or all those kind of things. Feed them into this pure function that also takes the previous game state, like the whole previous game state data type, and then returns a new game state data type out the other end. So that's the return value this side here. And that will be basically a copy of what we passed in with whatever changes had to happen because of the events in that frame. So this is the simple imperative kind of thing where you'd have your game state as a giant global variable, and while you're going, you poll for events and update it and then render it, that kind of sort of process. In Haskell, this is the way that gets represented. I'm not going to go into that too much, but this is just sort of the equivalent syntax. A while loop in Haskell looks a little bit like this. The fact that I'm using a let here, and it doesn't look quite the same as this line here, to assign the parameter means that this is a pure function. So this is the pure part, is updating our game state in the middle. So I haven't included time, right? So this is me coming up for a reason to use NetWire, and the big thing that you want to know typically in games, frame to frame, is how much time has passed to step your system. Because all the fun stuff happens based on time. To do physics properly, we need to know the time delta. All these kind of things happen because you need to know how much time has passed from one state manipulation, sort of, stepping into your simulation to the next frame. And NetWire sort of builds this all into its little functional calls, I guess, which is where this comes from. So I'm using this. We'll get into a lot of examples now about what control.wire offers in terms of building time-based simulations, which is essentially what the sheep game was.
Sorry, can I just ask, is NetWire, is it a Haskell library? Or,
yes. It's a library. I mean, it takes advantage of a lot of Haskell features, but there's no reason vast chunks of it couldn't be ported to anything else. In the end, it's a library of functions, and so this is the data type for wire. So this is a little bit like in C# or Java, something that has 4 type variables. So wire is the type, the class name, I guess, and then it has these 4 type variables. And we'll get into what each of those kind of mean, and then what wires can sort of do as a result of that, I guess. So at their most basic level, wires always produce values, right? So wires are the bit on the inside of your system between the 2 imperative cores. So a simple wire might do nothing, right? Takes in the last game state and spits it out without changing it. It's sort of just constantly doing nothing. But you always feed in your initial game state and then get a game state back out again. And that's what this looks like in Haskell, right? A function from A to B, where these are type parameters. So they can vary, that can be ints producing strings out the other end. In the case of the game core, it's game state producing another game state out the other end. But then it augments all these values with time. So whenever you have a wire instead of a normal Haskell function, time is being fed into it as one of its parameter, and time is the delta between the stepping of that particular wire in the simulation. And then what wires can do is they don't actually always have to produce values. So this either data type is a bit like throwing an exception, but much lighter weight. So essentially what this is saying is that when we feed in time and we feed in some input, then we get back either some error type or we get back the thing that we really wanted. So wires don't have to produce values every frame. That's how you do things like, you know, lightning. You don't want, if you want to have a wire that produces lightning occasionally, you're not going to want it to produce every frame. You want to represent the fact that lightning happens sporadically. So it'll error most of the time, and then occasionally this is a machine that's going to spit lightning out. So like the stars sort of appearing in the sky, they don't appear all the time, but occasionally a new star gets pumped out of the system. It gets a little bit more complicated now. These are all the features, I guess, that you get with a wire. This is what all those types kind of mean. Now we're returning a pair of things. Instead of just returning the error or the value, we're also returning the next state. So wires sort of encapsulate the idea that you don't want to be running the same, you don't want to be stepping the same state every time. So with the slides, right, going back and forward on slides, each one of these slides is a running wire, and when it changes, it produces a new wire out the other end. We'll see a few examples of that, I think. And I'm going to skip over effects because they just sort of complicate it where I need to use that too much. That's how it changes. But let's look at how the sky gets built, I guess, in the sheet battles game. So to build it up, I needed a few things. I wanted to know what time of day it was so that I could change the colour of the sky. You know, based on nighttime, I've got a night colour, and daytime, I've got a daytime colour. Some interpolation going on there. And the stars, I only want them appearing at nighttime. I don't want them, disappearing through the next day. So what I can do with these slides is I've got sort of code down here, and this is the code. This is the value that's being produced by that code out at the end of it. So this is my, I guess my inner functional core, right? This is the value that I'm using, and then this is producing values every frame that I'm just sort of feeding in and displaying up here, just by reading the text. So this is a very basic wire that comes from the library called time, and it tells me the number of seconds that have elapsed since I started running the simulation. So if I go back a frame back again, it resets because that wire gets sort of restarted and then it sort of keeps stepping itself.
So have you actually put together this presentation using NetWire and SDL?
Yeah.
That's pretty cool.
Yeah, I can show you just to prove the point. So where are we up to time? That wire there. So this is the code for the presentation. Sort of a list of slides, and at each point I can show code and also run the particular bit of code at the same time to kind of step through. Yeah, so this is the other app that I've done with this. As I was sitting down and write the presentation, I thought, well, I've done this, one weekend. The BFPG is like 60 people or 50 people, or whatever it was, and I felt like I should do a little bit more practice before I started telling people, this is a great way to do things. I should actually figure out if it works more than, for more than about 24 hours at a time. So down the bottom here we've got time, and it is a wire that doesn't care about any of these three things, but produces time out the other end. And what these type variables, if it doesn't care about any of these things, it means it can't do anything with them. So given it doesn't care about what the input is, it means it doesn't really take an input, it sort of ignores it. So you're feeding in input, but it can never actually do anything with it because it never knows what type. And in Haskell, very strictly, you can't use types that you know nothing about. So the fact it knows nothing about that type and doesn't produce it out the other end means we know that it can't possibly be using its input. Because there's no extra information about what's E here, we know there's no side effects. This E, because it knows nothing about what that E is, it actually means that it can't produce any errors. So because the type signature of this wire doesn't have any extra information about these, we can infer a whole lot of information about this without actually having to, I know I can run it, I can see what's going on, but just because of how strong this type system is, all that power we get means we can infer a whole lot of information about it. That's kind of why I ran through all those features that those type variables add, because it means when you look at the code, you can start thinking about which of those features are on and which of those are off for these wires.
So are you Is that a function, or are you instantiating any type there?
This is the function, well, that's the name of the function. So this is the separator for the type signature that goes out the other side.
But you haven't defined the contents. Or the
No, the
implementation.
function is time equals, somewhere else. Yeah.
So function signature looks good.
Yeah.
So now we also get a whole lot of combinators for chaining these wires together. So a very simple wire that produces time, and I'm feeding it into a wire called derivative, which does what you expect, right? It takes the value that's coming into it, a number, and then takes the derivative of that over time. So time is always going to be 1, right? The rate of change of time over time, dt, is always going to be 1. If we were to feed in, say, time multiplied by 2, and then take the derivative, we'd get 2 being printed out every time. So that, it's sort of a bit constant. But the idea here is that we can chain these things together. So I'm chaining time into a whole different thing that is, take the derivative of the value with every time delta and print that out. 2 separate functions, and we glue them together using these kind of operators. So here's a few more. So now, what I did in the game was I was sitting down to do the demo, and we have maybe 5 minutes, I think, at the end of the weekend to do the demo of the game, and I had the time starting at sort of 0. I think I had it starting maybe midday, the way the time shift works. Like, well, I wanted the sky to kick in kind of straight away as the stars start appearing. So instead of using time, I use another library function, time for 17, which just kicks it up to 17. And then to turn it into a real day cycle, this is another operator. Really, it's kind of fancy glue for plugging things together, right? So we take time from 17 and then we feed that into a function. So this is anonymous function signature. But I think you can work out what that's doing from just sort of reading the words, right? Given a t, take that t modulo 24, and we get a cycle that runs up to 24 and then round back to 0 again. So giving me the sort of hours in a day kind of thing. And it's all sort of separate, lots of little functions being pieced together by these little glue. And each one, you only have to think about each one on its own. I don't have to think about how the whole thing kind of works. So then I use this time cycle all the time. Take the time from 17 and then feed it into mod 24.
So that's a function definition, right?
Yes,
yeah.
yes, this is a function definition. So then I needed to know how close we were to nighttime to do the interpolation. So when I've got 2 colours, night colour and day colour, I want to know how close I am to nighttime to know how much blending to sort of do straight linear interpolation. So this is just an ordinary Haskell function called fraction to night that takes a parameter called hour, and I just take 12 from that value and take the absolute value of that and then divide it by 12, and that gives me at midday 0 and at midnight 1 and 0, sort of 1 as well, and that gives me this value here, which is where I can start feeding it into this kind of thing. So here's our time from function running at the top. Here's the fraction to night of that value running here. So as we head towards the middle of the day, it's trending down towards 0. I've got 2 colours. My start colour is nice blue, end colour is a straight black, and then I have this sky colour, which is the interpolation between those two based on some night fraction. So this is the definition of that function here. The sky colour for a night fraction is the start plus the end minus the start times the night fraction. So I'm taking advantage that in Haskell I can treat sort of tuples of numbers as a number in a vector space. So there's a color is really sort of three-dimensional space. Color could be mapped onto that. So I'm using that to sort of do these kind of and then that's a vector scale, the scalar on that side. The 2 colors there.
Is that kind of a standard Haskell thing? Like basically, if you've got, does it work with lists as well? If you've got like a list of things, can you apply the operators?
No, not implicitly.
Just tuples.
Yeah, and that property comes from the library that I'm using, NetWire. NetWire brings in sort of vector spaces using tuples as a first class kind of thing. And it just so happens that with all the basic building blocks you get with Haskell, it all just kind of, with a few tweaks, it all just kind of works. There's a way of extending types in Haskell. There's a little bit like extension methods in C#. or implicit objects in Scala, if you've done them, that lets you sort of add functionality to classes without being at the point of where they're kind of defined, which is where you have to be in Java and C++ and things like that, I think, unless things have changed in 11. So then these are all the three components to the background. We want a Y that cycles time from 17 and then mods 24. We want something that gives us the fraction tonight that we are. We want something that interpolates the sky. And then we want to just feed it all together. So take the sine cycle, feed it through fraction tonight, which means we've now got, at this point here, right? After doing those two things, we've now got a Y that spits out the fraction tonight instead of spitting out the time cycle. And then feed that into the sky color, which is a function that spits out color given night fractions. And at the end of this, we've got a Y that spits out colors. So we started from Y's that produce time, changed them into the Y's that produce fractions tonight, and then produced a Y that produced colors. And we can assign that to a value and use it. So that's just my two colors. And now we've got the whole thing kind of running. So this is very much what we had before, but the background's changing according to all the things that are going on. So this is our wire that produces color down the bottom. Alright, so it starts.
Can I just clarify one thing?
Yeah.
So what's the difference between a wire and a normal Haskell function?
It's the bit that it looks like this. It's really a wrapper around a quite complicated function, but because of all those features, you can do a lot of cool things with it. So a straight Haskell function would just be A's to B's, but because of all these different things, it can, and the fact that everything takes time, you can write a really nice library around functions like this. I don't know if there's a nice way to, I'm not sure what the analogy might be.
Is it like a library for dealing with time-based data conversions almost?
Yeah, absolutely. The assumption is that when you're building stuff with wires, everything you want to do has time as a component. So you always get time available. And once you add time as a component, these kind of things, the fact that you're not always producing at every time instant, you're producing at some instance, and then the way you can sort of modify functions, I've got a few examples of that coming in, the way you can modify functions according to time as well. Yeah, so the stars, the next bit of the sky, so we've got the background changing over time. The stars, essentially what happens is they get added through the evening and then gradually dropped off through the morning and then removed completely, once we hit about 5 a.m, there are no more stars in the sky. So, but it starts off with the same kind of things we built before, so we're still using that time cycle, using all that code, lots of little functions, etc. to feed in here. But what I want to do is join it together with another wire that produces a random star. So what this does with this NNN kind of combinator is says whenever you get an input, split it and feed it into two different wires at once and then collect up the results at the other end. So when we get our input coming in, at one point we're stepping the time wire, which is going up in seconds, and at the other point we're feeding it into a random number generator, which is generating a coordinate for a star to the out, and then feeding that back out. And what we're getting out is actually a tuple of those two together.
Is that a standard Haskell operator, or is that something that's defined by wire?
Somewhere in between. It's defined you can do this with functions as well. So if you've got a function, from A to B and a function from A to C, you can use this and to turn it into a function that takes in A's and produces a B and a C together.
Okay.
So this is not a function from NetWire, but it's just taking advantage of the fact that, for functions you can do this kind of thing. And
is that what you'd call functional composition?
Functional composition is more the triple greater than.
Okay. Yeah.
I can actually write that using the DOM, which is functional composition, which reads more like f of g. That's more. These are all, I guess, combinators on how to join functions together, but in very particular ways, in very sort of type-safe ways that keep them separate, and then So it works for normal functions, but it works with wires as well, because wires and normal functions are both types of the same kind of thing. They have a lot of things in common, even though wires has all these extra features available. They can be treated like normal functions for the purposes of this thing here. So this is probably the most complicated bit of code we'll see, and this is how the star system is defined entirely. So stars is of type, so that's the type. This is the name of the function, and this is the type signature of what we're returning. Because there are no arguments that come in, we're just returning one of these. So a wire, we don't know anything about E, so it never inhibits. This means it has no effects because we don't know anything about what that M could be. I could write any letter there and any other letter here, and it would all still work. The first thing here, these are the parameters. So we feed in time and a position for what may or may not be a new star. And every instant, it's going to spit out what the position of all the stars at that instant are. A QM is a wire library. It comes from the standard library. It's for doing sort of state manipulation. And so this lets us do sort of state internal to the function that it's not mutable, and it does change over time, but it changes because when wires produce, they also produce a new copy of themselves to run next time. So that new copy contains the new state that will be sort of looped back up in. So the initial state is empty array. So originally we got no stars, and then it runs this every frame, and it says this is the last state, and this is the input. And I'm matching. So this is using pattern matching, which is available in a lot of languages these days, to say that if the hour is after 5:30 in the afternoon, add new star to old stars and return that as the full set of stars. If the hour is before 6 a.m, then if old stars is empty, then just return old stars. Otherwise, return the tail of old stars, which will essentially drop one element from that list. So if it's before 6 a.m, in this step of the game, we're going to remove a star. So we pop one star off every tick. And if it's after 5:30, we add one star on every tick. Otherwise, we clear out the whole set of stars and only return an empty list. So that way, outside these bounds, which is going to be after 6 a.m, before 5:30, this function always returns empty. So you sort of get that, you can see what's going on here. So time cycle feeding through. This is the count of the number of stars. Stars start adding, stars start going away as we approach 5 a.m, and then 6 a.m, whatever it is, boom, they just kind of disappear at once. It's because the number of frames are not, it doesn't balance with 5:30 and 6 a.m or whatever I've picked. So there is a kind of destruction of a whole lot of stars at once that happens there. And this just keeps running forever because that time cycle just keeps circling around. So I've had to shorten the name here just to sort of see what's going on. But this is the code that's running here. So we have time cycle and random star running together, producing a pair of values. And we know that stars is a wire that takes a pair of values. So all that has to line up at this point, otherwise it wouldn't type check and it wouldn't run. And then we feed that into something that computes the length. So that's what I'm using to spit out this here. So at the same time, I'm actually taking this part up to there, to the end of stars, and I'm feeding that into something that draws rectangles at every star position to do both of those sort of displays at once. So then this is probably a bit more complicated. This is how the star system is written inside my original code. And this is it running in the background as well, with the colours and the stars appearing and disappearing. I wanted to show that I can define from all those simple, well, maybe not so simple, but all those little building blocks, right, that are all very separate. Time cycling, sky colour wire, the stars wire. I can produce sort of a more complete wire. So rather than in my final sort of top level function for doing this, I don't have to refer to all those little bits. I can build up a bigger bit that is the sky. So up here I've got, this is like a class definition, essentially saying that sky is a class called sky that takes colour and array of positions in its constructor, and you're always able to access them later on. So positions array of in pairs. So sky needs colour and an array of positions. Now I can, down here, I can say I've got a sky wire that takes in time cycle, uses time cycle and feeds those values out into this thing here. So now I've got a couple more crazy operators. But essentially what they do is they say, here's the constructor for sky. Instead of constructing it with like normal values, which is what you normally do, right? You'd say, new sky, here's my color, here's my set of stars. You say, I'm constructing not a regular piece of sky, I'm constructing a wire that produces skies using a wire that produces colors and a wire that produces stars. So without having to write any special code specific to producing sky wires, I'm taking advantage of that sort of auto lifting of things. So these are not regular values, they're special sort of value producing wires that I can almost treat like a regular value as long as I use a special bit of operator kind of language, I guess. The way I read this these days in my head is almost as though they don't exist, you know? Because if this was a regular value that had the same, that was just color, and this was a regular value that was just a set of stars, this is the same syntax and it would all just work. So this kind of, you know, it looks a bit complicated with all these kind of operators going on, but once you get used to sort of reading it and realizing that this is really sort of just representing a little bit of extra, not quite as important as it might seem. So anyway, that's that bit. So at the end we end up with a wire that produces sky objects rather than a wire that produces stars and a wire that produces colours. And at the end I can just have a wire drawing function. So lots of tiny little functions feeding together with all sorts of different glue. The good thing about Haskell with all that glue is that you can't get it wrong. Basically, if I was to use the wrong operator, the whole thing just wouldn't even compile anyway. So there's no sort of worry for me there for those kind of things. It's very quick to develop and test these kind of ideas because everything's very small. So getting sort of visual feedback going.
If it needs help with the door there, it's stuck.
Just the chair already in here.
So it was really quick to sort of prototype and play with these kind of ideas because the code, it's very easy to go exactly to the place you want and change it and know if it's all kind of worked. And then I sort of had file watching routines going on that would recompile everything very quickly, kill my running game process, restart it at the point I was. I don't know if anyone's seen Brett Victor's talk. He did a talk on tooling, I think it was using JavaScript maybe, an editor where you have like your running app and you change your code live and you sort of see it. I had almost that kind of system going on just by killing the process and restarting it. And the Haskell compilation is fast enough that it's almost live, I guess. So that was pretty cool. All right, objects. So I ended up spending probably the first, so Camp.js was about 3 days, I think, Friday to the Monday, maybe 2 days. I'm not spending about the first 12 hours or so, or almost the whole day, doing all this object code for moving things around. So, you know, velocity functions and feeding acceleration in and getting the position by using all the movement equations and all that sort of thing. And then, on like the Saturday afternoon, I discovered this object stuff that already existed in NetWire and had everything I kind of needed. So, and I got to throw it all away. And yeah. I knew someone else's code, which was good, but I just spent, you know, like 12 hours of a 2-day hackathon doing something I didn't need to. So objects in NetWire are wires, not objects. These are not objects in a sort of classical programming sense, more objects in a physical sense. So for us, an object is a wire that never inhibits, no effects, takes in changes to itself, so that's what this object diff thing is, and then spits out state all the time, whatever the current state of the object is. So whenever you step the wire, you get out what the current state is. And what you want to feed it in is ways of changing it. So you can feed it in different accelerations, you can translate its position, or you can set its velocity. And what an object state is, and this is a data type declaration, is a pair of values, just one for the position and one for the velocity. They have to be the same type. So in my case, I use tuples of 2 doubles or whatever it is for this thing here. but it'll work with all sorts of things. So it could change to 3D space without actually having to change a whole lot of my code. And originally I had everything only happening in up and down, and I was only modeling sort of one dimension. But because all this stuff works across, I didn't have to change this portion of the code when I went to move to 2 dimensions, because it also works on sort of number spaces and things like that. Anyway, so that doesn't quite fit anymore. Here's my box, and that's my rendering of the position and its current velocity, which is 0. It's sitting down here, and this is how we instantiate it. So you give it an initial. This is a wire now producing values. So this is the rendering of the box wire over time. So this is actually producing a new value every frame, just happens to be the exact same thing every time. So feeding in its initial state, which is at that position, has no velocity. It just sits there. So now I'm feeding in some sort of acceleration into it. So this box is the same as the box from before, it started there. And I'm saying, this is a Y that produces acceleration, and feed it into box. So this is the same as doing the time cycle stuff, but this is a Y that produces acceleration. And the way this reads is basically all the time, produce acceleration 5 minus 5. And it does that. And slowly it steps up into the sky. So the actual sort of box, the object manipulation is completely separate to the way that you produce the values that change it. So I can wrap all that sort of movement logic up in just this tiny little thing. And then for the game, all I had to worry about was turning my inputs into these accelerate types to produce the thrust in the different directions.
Is it much harder to apply that to an array of boxes?
No, not harder at all. I mean, if I had an array of boxes, I could, you can sort of lift this thing and say, instead of being one object, be many objects, feed all these accelerations into lift acceleration to be many accelerations instead of one, and it kind of works out, yeah.
You could probably map a function on a list, like I think Python does.
Yeah, exactly. It's exactly the same as mapping over a list. Yeah. Right, so here's a slightly more complicated example. So we can see the box shooting off to the side. And this is all the code to produce that. So this is the same box as before, starting in the bottom left. And again, I'm just feeding acceleration into it. But what I'm doing is I'm changing what the acceleration function is. And I'm using a whole bunch of new functions that, this is where I say there's sort of functions that work on time. So, let's go back here, come on. Right, these arrows are sort of saying, do this bit until it starts failing, and then do the next bit. And then when that starts failing, do this. The arrow is a combinator that takes 2 Ys, and then knows how when the first Y starts failing, always produce the second Y. So first Y gets chucked away. So it's how you sort of chain actions together. You use this one here. Rather than what we saw before with the angles, all 3 together was for feeding through. This is saying, do this until it fails, and then do this one, and then do this one. So how this reads, we allow an input for 5 seconds to produce pure acceleration. So for 5 seconds, of nothing, sorry, to produce no acceleration. So for 5 seconds, produce no acceleration, and then fail. So that's what that line does.
What does the pure do?
Pure is saying, it's wrapping what is a value up in as sort of like a constant wire. So, usually wires take input and produce output. Pure is the function that says always produce this very particular output, and don't worry about your input or any other kind of things that are going on. So for 5 seconds, do that acceleration. Then for 1 instant, do fairly massive acceleration that way. But it only happens for 1 tick. So there's a whole bunch of functions that are like this. And there's an instant variant versus a seconds kind of variant. So for 1 instant, give it a huge boost. And then after that, apply acceleration of 0 and 50 forever. So that sort of tracks it down, sort of gravity kind of path. Yeah.
So these operators, like the arrow ones there, are they something you can actually define yourself?
Yes.
In Haskell?
Yeah, so there's not really, they're very, no, that's not quite true. I was going to say there are no taboos against using operators in Haskell. There are some taboos, but these kind of things are fairly, well, this sort of arrow sort of chaining, because it works for normal functions as well as for wires, there's a whole, it's actually called a category, so there's a whole group of things that are a category that can work with these kind of operators. So these operators are as common as plus is for numbers, right? So plus works for integers, it works for doubles, it works for floats. This works for functions, it works for wires, it works for a whole bunch of other types of things as well. So it's sort of well known.
It's basically a Lisp syntax, is it? Because it's all like lists of items, and so your operators are just another item you can define in a list of objects of your operator. Is that right? Just all the bracketing as well seems very. You might not know Lisp, so.
No, it's not quite the same. Bracketing's there. I normally actually write this slightly differently. The bracketing's there because that's how the parser sort of has to work, but mostly because I've got lots of tuples, there's lots of brackets. And I'm ignoring a key piece of information with the way this object stuff works, and that you pass around a world state, which is what that last pair of brackets is. I'm ignoring any kind of world state for manipulating the object, which you'd actually use for doing collisions and things like that. No, it's more like in Haskell there's no special syntax really for operators. The operators, you can use whatever symbols you want. And you can use other words and use them infix as well, as long as you put backticks on them and things like that. So, yeah. I forgot about this one. It doesn't even work anymore. It doesn't work anymore. Oh, what a shame. So this was showing how I could actually do some live, I don't know, I'm lost, shifting of the object. So this is code that interrogates the joystick, and then, so instead of having what was essentially constant acceleration, changing over time, this is changing the acceleration. So again, the same function to produce the actual effect, right? Box gets fed acceleration. But in here, instead of feeding it straight acceleration is actually equal to the thrust with a particular joystick, where if the joystick's button is down, then we accelerate it up, otherwise we accelerate it down, according to gravity. So let me do, what is a very disappointing demo now. What a shame. Yeah, so that's kind of the end of objects.
So you can set up global constants as well?
Yeah. Not in, I don't know if you're thinking about with the joystick there, I had to feed it all the way through down my slides. So I don't have the joystick get a handle.
So if you want gravity constant throughout the whole...
Gravity constant is fine.
Yeah.
Yeah, because it's constant at compile time.
Yeah.
If I wanted to read my gravity constant out of the file, generally I'd have to read it and then pass it all the way down to where I would need it. So it would have to be more dynamic than that. Yeah. So all the constants in the sheet battles game are all in a particular file that is a Haskell file. But Haskell's very succinct, so it all just reads as color, day color equals a tuple, and it sort of looks like a config file anyway, so there's no point to pull it out. So I had a few problems, I guess, and this was particularly hard to understand as to how functions get changed, how the sort of time gating sort of happens, I guess. So you can see this. So I gave this to the BFPG. So this is saying BFPG, cycling through a BFPG in order. And what it's doing is every half a second, cycle from that array. So pull one of the values off what is essentially an array of characters. In Haskell, strings are an array of characters. But if we were to flip that around, all this would still compile. If we were to cycle BFPG and then periodically every half a second, look at what the value is. So we get sort of a more random sampling of it. So that's what this one is. This is sampling. So cycling happens every frame. Every frame it ticks around, and then it feeds those values out. And what this says is only allow one of them through every half a second. Well, the former one says, well, whatever you're getting in, only allow it through every half a second, which means only every half a second do you do the second half, which is the cycling. And I can explain that now, but I didn't grasp this at all for like the whole weekend I was doing that work. It was really, it wasn't until I was like, hey, I've got a problem slide that I need to do, and this is a real problem for me. I wrote the slides like, oh, that's what it means. Right. So yeah, the first thing always gets fed input, and then this bit samples input, while this samples the input and then only does that occasionally. So getting your head around how all that kind of works, because these functions are really cool, like that for function I used, doing something for 5 seconds, do something for 1 instant, there's more, you know, do something every second, do something every 3rd instant, all that sort of stuff.
What's the input in this case?
The input, because they don't actually depend on input, I'm feeding in.
So it's a null input.
Yeah, null input, yeah.
Yeah.
Because cycle just reads off the array and spits the value out and discards its input each time.
Right.
So, and the whole, all of these demos have kind of worked like that. Whatever's on the far left-hand side, I'm feeding a null input into it and ignoring it.
And how is the periodically function getting the global time? It just
That's the other thing it does. So the way you call, instead of the very, you know, sort of the while loop that I was kind of using the original Haskell, use a couple of wire functions that track that. So they get fed through the time delta at every frame step. So, but it all just gets wrapped up in net wires. It almost has its own loop, I guess, that you call with your wire.
okay. So the functions aren't push only for values. They can kind of pull values as well.
They get told their input and they get told their time delta each time. So they get outside, this is back in like imperative world, there's a sampling of the time delta.
I see. So periodically is almost like a closure for this frame. Is that right? It encapsulates the time delta in it. Is that what's going on?
It encapsulates some timer inside itself, but it gets fed the delta. Oh, sorry. When I say I'm feeding in a null input, it's feeding in both a null input and the time delta since the last frame.
Oh, okay.
And so but that's all kind of handled through NetWire's machinery. I don't have to worry too much about determining the time deltas and things like that.
Okay.
It does that. On inside itself, it'll be tracking, it'll have a what is essentially state. That is how long since I was last called. What was my last, add myself to the delta. Am I over my threshold? If so, fire. Otherwise, error and don't fire.
I can sort of see how this ties into the functional reactive programming now. That's sort of like you're treating your application events as kind of like an infinite loop of things that just keep coming, and as soon as they come, they sort of feed into your pipeline and gets chained through a number of other processing of that event to achieve something.
Yeah, absolutely. Yeah, and it's all those four functions that even for 3 seconds, for 6 instants, every third, all that sort of stuff. That time, and I haven't used it enough, I don't think. These kind of functions to sort of gate how your system runs, to stop it running in certain parts for certain periods of time. Yeah. Like the way I've done the night sky, where it looks at what the hour is inside that wire. A better way for me to do that would be to have a wire that only produces random stars between the hours of 5:30 and 6 a.m. And that and decouple that from the fact that at the moment there's a kind of relatively big function that does the checking of the time, the adding of the new star, or the dropping of all the stars. Those are kind of 3 things that I could split out if I knew how to work with these a little better, like I do now. The other problem I had was any particular wire can actually do a whole lot of things because of all those features it has. So, and this harks back a little bit, like working out whether or not a wire is shutting down or not can be quite difficult, and where it's shutting down. So this wire is shutting down at the end of here every half a second. Well, after it produces on the half a second, but then shuts down all the time. While this one shuts down here, and sort of debugging where that happens, if you're unfamiliar with how these functions work, is really hard. So tracking where the errors, which is the shutdowns, happen, can be tricky. Lots of debug printing. State, I don't think I really actually had too many problems with that. Every wire can encapsulate its own state. It is local, but it's still there. If you end up doing FRP, any functional reactive programming things, one of the things that's different about NetWire is that every wire takes inputs. In traditional FRP, there's sort of 2 different classes of things. There are things that produce inputs, and then there are things that can consume them as well, and maybe another type or 2 as well. So those sort of things are partitioned, and you deal with one or the other. While in NetWire, it's all sort of jumbled up. Everything can consume values and produce values at the same time. So working out what that, when things were actually producers or consumers was tricky. And theoretically, you can actually pass effects through everything as well. I avoided that by not carrying a couple of these was, essentially. So if you're actually going to play with this, getting it all to work on recent OS X has been quite a challenge. It has gotten easier. There's some advice out there, and I can help anyone who's trying to do that. I'm happy to do that. But after Camp.js, I ended up wiping my homebrew setup and then spent probably a week and a half debugging why I couldn't get STL and Mavericks and Xcode and GHC and all this kind of stuff lined up in the right version. It was sort of hell. I'll post around some stuff to the list, I think, later this evening, some tutorials on doing this that probably explain from almost beginner levels how to get started with NetWire and STL in Haskell. The NetWire docs are actually really good as well themselves. The STL stuff I'm doing is just straight STL as you would in anything. In Haskell, the wire, it's very much just like using the C API. And in fact, with the sheet game, I ported it to OpenGL last week rather than using STL for the drawing. And that was again just like doing any kind of OpenGL, so it was painful. That's going to be, I think it's going to be the hardest thing with doing games in Haskell is the lack of engines, which means if I want to keep doing it, I'm going to have to start putting together, an engine essentially, and I'm not sure I have that kind of time in me, so we'll see. So all the code for the presentation and the game is up on GitHub. I'll send that round. And with the in combination with the functional group, we're probably going to try and host a hack night for doing, at least doing Haskell stuff. And I think playing with NetWire and drawing is really cool and a good way to sort of test out functional programming ideas. So if you're interested in that, I'd sign up to the BFPG list. I'm happy to cross-post it to KDM if that's a thing people are interested in. But I think that'd be, there seem to be a bunch of interest in that, so we might do it here. In fact, there's a really good location at some point, another day. Just to give people a bit of a boost, because there are a lot of people who've started playing with Haskell and functional programming, so we get stuck at the, well, what do I, actually want to play with now? Heading to Camp.js and writing games is a good idea, but they're not all the time, so we'll do something. And I think that's it.
Can we have a look at your the imperative code? Like how you could, is that all done in Haskell as well? At the edges of it?
Yeah. So if we call this is I guess highly declarative. This is all the slides. So this is the file where I have to find all my slides in. So you can see lots of text, this is essentially every section is a list of slides that I stick a little icon in the top right of. Like this one here. These are all the slides. With a slide, I can compose two slides together. So all these bullet points where I'm showing code as well in the next step. So I can I've got that separate and join it all together. But then over in the dirty main function, the drawing is, sort of draw string white using a particular font at a particular position. Main is the string in this case on that window, and sort of those are the two lines that draw a subtitled slide. Or for doing the code rectangle, so paint black rectangle down the bottom, then draw a string at a particular point using my code font, that sort of thing. So that's the rendering, and this is pretty simple because I'm only drawing text. Over in Flying Sheep Battles, and this is all pretty raw. So it looks much like any beginner sort of OpenGL does. So this is to paint a rectangle. Start drawing some quads, set the color, draw each vertex, and just kind of keep going on from that.
So the do keyword that you have there after the equals, is that
Yeah.
does that make it like impure or imperative or something? Or?
That makes it imperative. That means every line of execution after that, the order that they happen matter, and it sort of sequences them up. Because in typical Haskell, the order of execution is not necessarily guaranteed if it doesn't have to be. So there's lazy evaluation going on. So if you have a function, I don't know, call it that, x equals 3, y equal 2, z equal 1 in y plus z, x is never going to be evaluated. So if x was actually very expensive to compute, that would never happen, and only y and z would be computed. And they actually wouldn't actually be computed at this point either. It would only be computed if xxs was required to be computed somewhere. So there's the fact, and then but when there are effects involved, you know, if 3 was actually writing out to the file system or something, and we wanted to make sure that happened, well, it's going to be discarded here and we'd lose that. So you start using do notation to enforce that. This line happens, then we in an SDL, then we set the clear color. And it sort of every time you have a line in do notation, it's just like doing semicolons in regular languages, I guess. It just means that every line comes after the other. But essentially what it does is it keeps building a computation that wraps all the previous ones up too and makes sure none of them are lost. And even in the presence of laziness, all your effects are kind of fired each time. So.
Has the lazy evaluation ever bitten you in any way, or like something expected to happen didn't happen?
No, not really. No, I haven't got that far. It does bite people because you end up when things are not necessarily evaluated, they still have to be in memory. So memory usage can bite people. So if you've got a large sort of tree structure and that you build, and then you want to summarize it down to the average of all the values in the tree, for example. If you never force the average, then that tree is going to stay there in memory, all those values, even if you're only passing the average around. So if you never force the computation of the average, you've always got all the data that will eventually produce it available. So that kind of stuff can bite people. I haven't done enough programming at that kind of level with it. I've done a little bit of web app. I've done web app stuff with Haskell. I've done a lot of command line utilities with Haskell.
What do you use, like Fay or something like that for the web app?
Yeah, Scotty. A little bit. Oh no, so not Fay. That's the client side stuff. I've used Scotty, which is if you're a Ruby guy, you might know Sinatra. Sort of these tiny little frameworks. It's just a little web thing that you serve static pages, APIs, and does a pretty nice thing. So, yeah.
With those gotchas you mentioned, what are the tools like what are the tools available to you for profiling and debugging in terms of discovering when you're carrying around a lot of stuff you don't need to, or when you're doing a lot of work you shouldn't be doing?
I haven't done much of it, but the tools are supposed to be really good, the profiling tools. And there's a tool called ThreadScope that'll tell you how much work each of your threads are doing when you start doing. So how much work your system, how much memory you're using, how much work each of your threads are doing over time, and it will give you a breakdown by functions in terms of time and things like that. So they're very good. I was using just print line debugging basically. I would feed when I built so the way these arrows, those wires build up is you build like a flow diagram, I guess, in code, but you're building a flow diagram where values are coming in, they're splitting and going around. And I just had a wire that would print out whatever value was at the point, so I would just splatter this kind of this debug wire through my data flow diagram, then run it, and I could see where the values were coming out or not. Because at the point that we'd shut down, as long as I had sort of my tracer, my debug wiring before that and after it, I could find that point. So.
Are you able to, you had that slide where you had the sort of fallback wires after each one, and you had the 4 or 5 seconds of nothing and then the next one. Are you able to say like breakpoint the second wire and then run until you hit that and then go and have a look at whatever it's doing? Yeah,
you can set breakpoints. I've never done it.
Right.
I haven't tried. It doesn't come up as much. That kind of debugging. It's been interesting using NetWire for all those reasons where you have all those features available. It's hard to debug. That doesn't usually happen in Haskell. So it's usually very clear about what's going on in your system because of because of the type system and because you sort of limit what can actually be happening at compile time, that, you know, I've never reached for the debugger in Haskell, where reaching for the debugger on iOS is something I would do, you know, all the time to figure out what's going on. It's just a different way of approaching the problem, I guess. Yeah, maybe it would have been better for me to do that here though, but I haven't learned the tool. There's very little IDE support for Haskell. There's lots of editor support, but it's not like I can fire up Visual Studio and then set Visual.
I was playing with an IDE yesterday. I think it was called Lexa or something like that. You heard of that?
Lexa. Yeah.
Oh,
Yeah,
that name could not
yeah,
make it.
yeah.
I'll put a link to it online. It's pretty cool. It's got debugging support.
So it doesn't it?
Yeah, it seemed pretty sophisticated, really. Yeah.
Yeah, it's good because it
I was
gives
struggling to figure out how to write a function. It's
you got the editor guy.
Yeah, yeah.
That's half the battle.
Yeah.
Yeah. No, it's good because it'll give you, you know, like a module hierarchy, you know, sort of Ucode and all that sort of stuff as well, and links to the documentation and things like that. And there was a Visual Studio plugin for a while because Haskell's backed very heavily by Microsoft. So a lot of the top Haskell compiler hackers are employed by Microsoft to do various things. So
Do they fund it or something?
yeah,
Mhm.
well, yeah.
Is there any support for runtime code modification?
There is. It's called something. I can't remember what it is. Yeah, so you can, you know, for things where you might want to have your config file in Haskell, you could be dynamically reloading it from that sort of thing. There's a famous chatbot called LambdaBot that's in the Haskell IRC channels that knows how to sort of interrogate Haskell functions and tell you the types of things or tell you the source of something in the standard library, and it's used quite heavily, but it has that built into it as well because it does like hot code compilation and running in itself, and that all required.
Coming from a C++ background, and it's like a very static language, and it's once you've compiled it, you can't do much with it. Moving through C# and now to kind of more dynamic and functional languages, it's just amazing. Like, having a sort of a language console like in your application or something like that, where you like a little REPL environment where you can change stuff and type in new code. It's just an amazing way to work.
I mean, GHCI is it's a funny thing with Haskell. It's easy to say there's not much tool support because there's no real IDE that you reach for to go and use it. But if I go into this into the REPL, I can load up. I can probably load up one of the files. I think if I flag it properly. And look at, really investigate what the type of different functions are and the kind of things I'm using. So, and also run my code straight from here. So the REPL becomes, I can look at what the type of 1+1 is, or type of tail.
Do you use that a lot, like in your day-to-day work?
Yeah. So using GHCI the REPL comes in pretty handy. There's a tool for searching via type, which is amazing once you start using it. Yeah, Google. Someone mentioned mapping on lists. So you can take a list and a function and produce a new list afterwards. So if I wasn't sure what the name of that was, given a function from A to D and a list of A's, I'm looking for a function that will give me B's at the end of that. So this is the type signature of map. And if I sort of produce a short list, that will tell me that in the prelude module there is a map function that matches that type signature. And I think I should be able to get coloring on here. I'm not sure why it's not giving it to me. Probably American. There we go. And that'll highlight sort of the bits of color. And if I switch the order of those functions around, it works as well. So that's what it's searched for, and you can see that it's matched the first parameter to actually the second parameter of the prelude.map, but it knows that all just kind of works, and if I just change my arguments, it fits together. So Google is probably the most amazing documentation tool I've ever worked with, because it solves that problem.
You're basically saying, search for all functions that take these certain types and return a
Yeah.
certain type and just tell me what everything that matches that.
Yeah, exactly. And you no longer search for, what is the name of the function that gives me all the unique elements of the list. You search for what the type of a function like that must have, and you sort of tell it what you want to do rather than look for the name of the thing. And that, yeah, rather than trying to work out what each standard library implementer has called all their functions, you can sort of search for them by this. So even when Haskell has a funny name for something, it's not quite as bad as it could be, because as long as you can kind of work out in your head what the type's going to be, you can get to it and find it.
Thanks, Nick. That was really good. Does anyone else have any questions or anything else you want to talk about, discuss?
Actually, just at the start there, I got the impression that like it just compiled down to the JVM or something, but if it's Microsoft supported, I imagine it is compiling to native.
It compiles down to native, yeah.
Has the platform support?
How's the platform support?
Yeah, like can you compile for Android?
Yes, through the native code stuff that you can do with Android. I've not heard of it happening too much. ARM only got really good support recently, like last 6 to 12 months or so.
Right.
You can now compile for iOS pretty easily, so you can build, particularly this kind of like the sheep game app that's only talking to OpenGL. Building a Haskell app for iOS is pretty feasible these days.
If Android just happened to get support 6 months ago, it's all LLVM based, I'm guessing, because that's back when LLVM kicked in for Android.
Really?
iOS would have.
There is an LLVM backend for GHC now as well, so that might be the case. Yeah. But yeah, I mean Linux, Mac, Windows, no dramas. Windows is usually the hardest to get set up.
It's a surprisingly mature language, isn't it?
It's been going since the
20 years or
90s
something.
Yeah.
What's the performance like compared to C++?
Good. I think they aim for sort of within 2 or 3 times C++ performance. They're usually pretty happy with that. If you look at like the spectrum of languages, like expressiveness versus writing machine code, bare metal. In terms of expressiveness, Haskell sits at one end with like Lisp and Haskell at one end, and assembly codes at the other. And in terms for that kind of power that you get being at that end of the expressiveness curve, the performance is really good. I think that it's easy to forget just how far away from the machine you actually are when you're programming in Haskell. When you're doing the imperative stuff, not so much. It's very much that all compiles down to almost what you'd expect. But like the implicative syntax that's going on, all these wires and things like that, that's so far removed, and it doesn't do too badly. The code has to be written to work like that, though. In general, it's going to be a fair bit slower until you get to your tight spots, and then you have to write your tight spots in a way that looks a whole lot like C does to get it to run fast. Yeah.
Can you call out to other languages to call functions?
Yes,
Or,
there's a C FFI that's really solid. They're working on a C++ one and an Objective-C one as well. So they should be, and they're really close. They're both, one of which was a Google Summer of Code project that seems like it's going to survive, and I think the C++ one is coming out of Microsoft, I'm not sure.
How do you input the pentagram symbol?
What was that?
How do you input the pentagram symbol?
Input the pentagram symbol by using character viewer, and then that thing, and then putting your cursor in the right place and double clicking. But
Smart.
picking a font that has all the symbols was the trickiest part, because I didn't realize that most fonts don't have the full array of symbols. And what happens on your OS is there's this Apple symbols.ttf, which actually fills in all the gaps. So that's why I use Apple Symbols to do the symbol drawing, because it has all the different symbols, while most of the fonts that you use don't actually have any of that stuff in them.
I saw a lambda symbol in some of the code.
Yeah, that happens probably in here in the editor, where it's substituting. It's just Vim doing what is it called? Reveals, I think, where it'll substitute that expression, you know, a slash with a lambda if it matches the inner function, but it's actually a slash. It'll do it for sort of composition as well. Sort of turn it into a nice composition operator versus what is usually dot in. But full Unicode is available for all your Haskell operating needs.
Cool.
Yes,
Yeah, is anyone up for a coffee and lunch? Usually go in a cafe afterwards. You up for coffee, Nick?
For coffee. Yeah.
Awesome. Cool.
Let's do it.